Hi and welcome to another tutorial section on Kinemarc. Right, so this is on three-phase three-wire system. So in this system, three-phase three-wire system delta is used to normally supply power to balanced or unbalanced three-phase loads such as motors. And we can see from the diagram that this has no neutral wire like in the three-phase four-wire system in star. This has no neutral line or neutral current, and normally we use this system or it is used in, let me say, transmission lines involving very high voltage distributions. Right, so we know that the phase sequence in three-phase is either ABC or 1 2 3 or RYB. So in this system I'm using the ABC phase sequence. So I can say that the load here, since this phase is AB, I can say that the load here is AB, and since this phase is BC, I can say that this load is BC, and I also say that this load is ZCA, like that. And it goes like this. I'll have a current like this, a current here, and a current here. Since this phase is AB, I can see that this current is called IAB. This phase is BC, so I can name this current IBC. This is CA, so I can name this current ICA. Very simple. And then I'll have a voltage here like this. This voltage is going to be AB because it is between this line and this line. And I can also say that I'll have a voltage here which is BC, and I'll have this one over here that is AC. And since this line is A, I can say that this current over here is A, this current here is B, and this current here is C. So very simple. We have in the delta that the voltage between this line is the same voltage across the phase. So in delta we say that the line voltage is equal to the phase voltage, and then the line current is equal to root 3 IP. That is in delta. So if I have a voltage across this phase AB, this VAB is the same voltage across ZAB. And if I have a voltage VBC over here, it's the same voltage across this phase BC. And if I have this voltage over here, that is AC, that is the same voltage across this phase AC. Right, so now back to the KVL equations. I can pick a loop here in terms of AB. Alright, so I will say that VAB, that is this voltage, is the same voltage across this phase. So, and on this phase I have a current and an impedance. So I will say that ZAB is equal to IAB VAB. That is equation 1. Now, looking at this path or this loop, I can also write an equation because this voltage BC is the same voltage across this phase over here. So I can say that VBC is IBC times the impedance BC over there. And I have this line voltage, that is AC, the same voltage across this phase, that is AC. So and on this phase I have current ICA and impedance ZCA. So I can say that voltage AC is equal to ICA and ZCA. So this is equation 2. This is equation 3. So now from this side you can find the phase current, that is IAB, IBC and ICA from these equations. And how we got them is very simple, using KVL equation, going through this loop, going through this loop as well, and the last one going through this bigger loop to get equation 3. So now let's see, we have the phase current, that is IAB, IBC and ICA. So now someone will say, okay, what about IA? That is, this is a line, this is also a line, this is a line. So IA is a line current, IB is a line current, and IC is also a line current. So now how can we find the line current IA? It's very simple. Look at IA. We are going to use KCL equations over here. So this is IA. If IA reaches this node, it should split this way and that way. But then we can see that the direction of this ICA is opposing the normal flow, which should go down. So I can see that IA should be equal to IAB. That's it. When this IA reaches here, it should split this way and that way, minus ICA. ICA is minus because of the direction, because under normal circumstance, when this IA gets here, it should go this way and that way, but it is coming this way. That is why ICA is negative. So the same way we can find the line current IB. IB, upon reaching this node B, should go this way and that way. But look, IAB is coming this way. That is opposing the normal flow of IB. We should have gone that way. So IB will be equal to IBC minus IAB, right? IC, similarly, IC upon reaching node C should split this way and that way, but then IBC is opposing the flow, so I can say that IC is equal to ICA minus IBC. So this is very simple. This is how to analyze a three-phase three-wire system in Delta. You need just these equations to be able to analyze questions under this one. So we will solve one example on this one, so that we will know how to do it whenever it comes in our exams or anything, right? So in this example, it says that a three-phase supply line voltage of 400 volts has an unbalanced delta connected loads as shown in the diagram below. So let me input the values over here, and we have this one to be 20 angle 20 degrees, and we have this to be 35 angle 90 degrees, right? So we have to determine the phase current. That is, this is a phase, this is a phase, this is a phase. So the current over there is IAB, IBC and ICA, and the line current we have IA, IB and IC. So we are also to determine the total active power and the total reactive power. So we know that in delta, the line voltage is equal to the phase voltage, so they will all be equal to 400, like that. So but then we should know that in three-phase circuits, the phases differ by angles. So the phase at A will have 400 angle 0 degrees, so they differ by 0 degrees, and the phase at B, they differ by minus 120 degrees, and the phase at C, they differ by positive 120 degrees. So here it's also going to be 400 angle 120 degrees, because the line voltage, that is the voltage from this line to this line, is the same as the phase voltage in delta. So that's why we places 400, 400, 400, but then the angles are different, right? So now we can find the phase current, that is IAB, IBC, and ICA. We can pick loops over here using KVL equation. We can say that the voltage between AB should be equal to AB, that is I, the current there, IAB, and the impedance ZAB when we pick this loop. So now we can say that IAB should be equal to VAB out of ZAB. For VAB, we have 400 angle 0 degrees, and we have ZAB to be 30 angle 0 degrees. So IAB is going to be 40 on 3 angle 0 degrees ampere. When we pick this loop over here, we can also say that we have VBC, because this is line B and this is line C. So the voltage there is VBC, and the current over here is IBC, and the impedance here is ZBC. So I can say that VBC will be equal to IBC times ZBC. So IBC, that is the phase current, will be equal to VBC out of ZBC. So VBC, we have to be 400 angle minus 120 degrees, and ZBC was given, that is 20 angle 20 degrees. So IBC is going to be 20 angle minus 140 degrees ampere. So I'll say that the last phase current, that is ICA, I can say that VCA should be equal to ICA ZCA. That is, if you pick this bigger loop using KVL, you can find ICA to be VCA out of ZCA. So VCA, that is this voltage, we had 400 angle 120 degrees out of 35 angle 90 degrees. So finally we can say that ICA will be 80 on 7 angle 30 degrees. So now we have IAB, IBC, and ICA to be our phase current. And then in the question we had to find the line current also. Line current over here is IA. But then IA, when it reaches this node, should go this way and that way. So we can say that IA should be equal to IAB minus ICA. But then we have the value of IAB over here and ICA over here. So we just substitute. So it's going to be 40 on 3 angle 0 minus ICA, that is 80 on 7 angle 30 degrees. So I'll have IA to be 6.67 angle minus 58.98 ampere. So IB, similarly, when it reaches this node, should go this way and that way. So we can say that from KCL, IB should be equal to IBC minus IAB. But then we know IBC over here to be 20 angle minus 140 degrees minus IAB to be 40 on 3 angle 0 degrees. So you have IB to be 31.40 angle minus 155.84 ampere. So the last line current is IC. That is this current. When it reaches this node, should divide this way and that way, but this is opposing, so this will be minus IBC. So IC should be equal to ICA minus IBC. at ICA we had 80/7 angle 30 degrees minus IBC, that is 20 angle minus 140 degrees, and IC should give us 31.32 angle 36.36 ampere. So we are also to find the total active power and the total reactive power. But then in finding the total active power, we know from this one that this is our active power, reactive power, and apparent power. So if you want to find the total active power, that is P should be equal to S cos phi, and the reactive power should be S sin phi. But then we know that S is equal to IB, so P can be VI cos phi, and Q is going to be VI sin phi. But then let's take note that this is an unbalanced load, so we can't use this formula. We can't use this formula. We only use this formula when the loads are balanced. So now if you want to find the total active power, we should find the power at AB, the power at BC, and the power at CA individually, and when we add them we should get the total active power. Since the loads are unbalanced, we can't use this formula, but then we should find them separately, and then we will get our total active power. So PAB should be the voltage at AB from this, and the current at AB, and the angle between the voltage and the current. So PAB, the voltage at VAB, we had 400 angle 0 degrees, and we had the current to be 40 on 3 angle 0 degrees, because the angle between the current and the voltage. So when you look at the voltage, the angle is 0, and for the current the angle is also 0, so the angle is going to be 0 for this one. And then you have your PAB, so PBC is going to be the VBC IBC, and the angle between the voltage and the current. So PBC, we know that the voltage that was VBC, the question was 400 angle minus 120 degrees, and then IBC, that's the current over there, was 20 angle minus 140 degrees, because the angle between the current and the voltage, so this is 120, this is 140, so the difference is 20 degrees. So when you compute this, you should get the power at BC, and the last one is the power at CA. Similarly, should be the power at, the voltage at CA, the current at CA, and the cos angle between the voltage and the current. So PCA, the voltage at CA, we had 400 angle 120 degrees. The current CA, we had 80 on 7 angle 30 degrees. So the angle between 120 and 30 is 90 degrees. So if you compute this, you should get the power at PCA, and you add them, you should get your total active power. Similarly, if you want the reactive power, that is Q, the total Q will be the QAB plus QBC plus QCA. since they are unbalanced load, we should find the powers individually. So Q at AB similarly will be VAB IAB sine the angle between AB. So QAB, VAB, we had 400 angle 0 degrees, IAB 40 on 3 angle 0 degrees sine the angle between the voltage and the current. So here is 0, here is 0, so the difference is 0. When you compute this, you should get QAB. So QBC should be VBC IBC sine the angle between the voltage and the current. So VBC was 400 angle minus 120 degrees. We had IBC to be 20 angle minus 140 degrees sine, so the difference between 120 and 40 is just 20. So QCA, that is the last reactive power, should be VCA ICA sine the angle between CA. So QCA, the voltage at VCA was 400 angle positive 120 degrees. ICA, I had 80 on 7 angle 30 degrees sine the angle between 120 and 30 is just 90 degrees. So if you compute all of this, you should get the reactive power at QA, QBC and QCA, and when you add them, you should get the total reactive power. Similarly for the total active power. Thank you.